Hello, my name is Simon Shindler. I'm a third-year PhD student in the Yang Lab, and I'm going to talk about how we use surface reactions to convert hydrophobic fluorinated polyacrylates into hydrophilic acrylic acid to make better Janus materials. Janus materials possess opposite and opposing surface chemistries. Generally, they're hydrophobic on one side and hydrophilic on the other, as you can see in the figure. One way to fabricate Janus materials is by floating a polymer-coated material on a reagent-loaded solution to induce a surface reaction on only the liquid contacting surface. Currently, though, we don't know enough about how the relevant polymer films react or how they might degrade during the reaction. Specifically, we're interested in the degradation of a candidate fluoroacrylate polymer, poly 2,2,3,4,4,4 hexafluorobutyl acrylate, or HFBA. We fabricate films using initiated chemical vapor deposition, or ICVD, and you can get more information about ICVD from our group website if you follow the QR code on the screen. We will investigate two ways of preventing degradation. First, grafting using trichlorovinyl silane, which covalently bonds the polymer film to the substrate, and second, cross-linking with diethylene glycol divinyl ether, or DEGTVA, which prevents the film from dissolving. We fabricate three types of films. First, grafted and cross-linked films. Second, grafted but not cross-linked films. And third, cross-linked but not grafted films. We do this to test the effect of grafting on the films during hydrolysis. Next, we hydrolyze the films by floating them on sodium hydroxide to replace the hydrophobic fluorine with a hydrophilic carboxylic acid and characterize them to determine cross-linking density, fractional conversion, and hydrophilicity. So moving on to our results, figure 2a shows that the uncross-linked films disintegrated during the hydrolysis reaction. This is because the product of the hydrolysis reaction is a soluble polymer, polyacrylic acid, and so as the reaction proceeds, the film slowly dissolves. Figure 2b shows that the cross-linked but not grafted films delaminated during hydrolysis. This happens because even though it was cross-linked, the adhesive forces between the film and the substrate are weak, and when it becomes hydrophilic during the reaction, the film peels off. Figure 2c shows that even after 3 hours in solution, the grafted and cross-linked films did not degrade, but did show some wrinkling. The wrinkling may have been caused by swelling of the hydrolyzed polymer, and it's not a problem for most applications. Figure 3a, moving on, shows the fractional conversion over time, showing that the hydrolysis follows a first-order behavior in the surface concentration of HFBA functionality. In other words, the rate of hydrolysis is proportional to the number of HFBA moieties at the surface. Figure 3b shows that there is a direct proportionality between the equivalent rate constant, calculated from the fractional conversion and time, and the concentration of sodium hydroxide. What that means is that the rate of hydrolysis is proportional to the concentration of sodium hydroxide. Figure 3c shows that the dynamic contact angle decreases uniformly during the reaction. This tells us there is a well-behaved change in hydrophilicity following the reaction, and that there appears to be a clear relationship between the dynamic contact angle and the fractional conversion. In the future, such a relationship could possibly provide a simpler way to determine the fractional conversion, because all you have to do is measure the contact angle. From this work, we're able to conclude that silane grafting prevents film delamination during reaction, cross-linking prevents film dissolution during reaction, and the rate of hydrolysis is proportional to the surface concentrations of HFBA and the bulk concentration of sodium hydroxide. These findings enable more control over the fabrication of Janus materials using these methods, and they give us some expectation of what is required in order to use these methods. They also may help us better understand the environmental degradation of PHFBA or poly-HFBA as a function of POH, or the amount of OH ions in solution, which is relevant to many applications of this polymer. I'd like to thank my lab and my advisor for their support, and I acknowledge the Cornell Center for Materials Research for help in the research. Feel free to pause the video at any point to read anything in more detail. Thanks for listening.